with inequations, we represent them on the number line. As we know, we can draw a dot to indicate the boundary, and then we say, okay, it's in between, and so on. If there's two variables, then the way we indicate them, of course, is on a number plane. So how do we indicate the regions that satisfy different inequalities or inequations in the number plane? First of all, we sketch the boundary. Same as with the number line, we would plot the point, which is the boundary. Now, if it's a less than or a greater than, we use a dotted line to indicate the boundary is not included. If it is included, then we would use a solid line. So the point of intersection is interesting. Is the point of intersection included or not? Now, it would have to satisfy both boundary lines to be included. So if one of the boundary lines is dotted, in other words, is a less than or just a greater than, then the point of intersection would not be included. And just like we do on the number line, to indicate it's not included, we circle the point and don't colour it in. And then we say, okay, we know that point of intersection is not included. And just like with the number line, we then test some points to see if it works. Then we know which side of the line or the boundary we are. So let's do a very simple one. Y is less than x plus 3. So the boundary is the line x plus 3. It's dotted because the boundary is not included. It breaks our number line or number plane into two sections. And so I just pick a number to test. And I always want to make life easy for myself. 0 is usually the easiest number to substitute in. I can pick any point I like as long as it's not on the line. So the origin would probably be the easiest one here. So I'm going to test 0, 0. Sub it in. 0 is less than 3. Is 0 less than 3? Yes, it is. So therefore, we include 0, 0 in our shading. So we would shade that side of the line. Our circle, x squared plus y squared, in this case, it's equal to, so the boundary is included. Again, it breaks our number plane up into two regions. Inside the circle, outside the circle. I can pick any point I like as long as it's not on the boundary. So again, I can use 0, 0. And 0 squared plus 0 squared is 0 greater than or equal to 9. No, it's not. So therefore, I'm on the outside of the circle. Now, this is a very interesting one. Y is less than the square root of 4 minus x squared, which is our semicircle. The boundary is not included. So there's our semicircle. Problem is, it's still just one region because there's no boundary line below the x-axis. And so if you like, it could sort of flow out and fall over. I'll test 0, 0, and I know I'm inside because yes, 0 is less than 2. So I know I'm inside. But as I say, what's stopping it flow out and around? There must be another boundary in there. And the other boundary is the domain. Because if I was to ask you what was the domain of this function, you'd say, oh, only between minus 2 and 2. So the domain stops it flowing out. Because if I was to test a point, let's pick something very negative. Negative 10, which is over here somewhere. And sub it in, I'd go, negative 10 is less than the square root of 4 minus 10 square. Oh, hang on, that doesn't exist. So clearly that point is not included. Notice the boundary line, though, in this case, is solid, not dotted. Okay? And that's because if you test a point on the end point of the domain, so let's pick minus 2 minus 2. Okay, so down here somewhere. If you sub it in, you'll get minus 2 is less than 0. And that is true. So the domain endpoints are actually included. Technically, this point of intersection, is it included or not? I haven't labelled them yet, but those x-intercepts, would they be included or not? No. Because if you sub them in, so minus 2, 0, you would get 0 is less than 0. Well, that's not true. 0 is equal to 0. I don't know if I did actually circle them or not. No, I didn't. So that was bad. I should have circled those two x-intercepts. I doubt very much anyone would penalise you for not remembering those ones, because that really is a technical point. But technically, they're not included, so we should circle them. All right, we can have more than one graph, which again will break it up into more regions. Usually when we've got one graph, it'll just break it up into 2 regions. More graphs will create more regions. I just do each one separately. So y is greater than or equal to x squared. Well, the boundary will be my parabola, and that one will be solid. Now, theoretically, that parabola keeps going off to infinity. So yes, it has broken it up into 2 sections. Now, I can't test 0, 0, because 0, 0 is on my parabola. So I have to pick a point which I know for sure is either inside or outside the parabola. So don't make it hard for yourself. You might say, oh, I'll pick the point 2, 7. But where is that in our graph? I'm not quite sure whether that's inside or outside the parabola. So let's stick with something on one of the axes and we'll know. Which point did I pick? I picked 0, 1. 0, 1 is definitely inside the parabola. And if I substitute that in, yes, that works. So I know I'm inside. Now, I'm not going to shade the inside right now. What I'll do is I'll just mark in some crosses there so I know, okay, I'm inside the parabola. Now I'll do the line. There's y is 3x plus 4. And I'm going to need those points of intersection. I usually ask for those. So we can solve them simultaneously. Works out x is -1, x is 4. So there's my points of intersection. Let's test a point. I can use 0, 0. 0, 0 is not on the line, so I'll go back to using the easiest one I can. 0, 0, is 0 less than or equal to 4? Yes, it is. So I'm going to get a different colour cross. I know the region I'm looking for is where I have both the red crosses and the blue crosses. That's basically why I used a different colour. So I can very visually see, oh, okay, I know the section I'm in. I'm in there. So there's my region. Okay, 3F.